thank you for coming to my talk. I'm Tim Taylor, and this is the importance of open-endedness for the sake of open-endedness. This is just a short 2-page paper, but it came about in response to 2 papers that were published last year in the Artificial Life Journal special issue on open-ended evolution. One of those papers was Aaron Hintze's Open-Endedness for the Sake of Open-Endedness, which presented a simple computational model of open-ended evolution. The second paper was my own, called Evolutionary Innovations and Where to Find Them, which presented a framework for discussing models of open-ended evolution. So in this current contribution, I just want to apply my framework to the discussion of Aaron Hintze's model. So I'll discuss his model in a little detail later on, but he concluded that we needed a proper definition of complexity and diversity for rigorous hypothesis testing, and that we should not engage in the quest for open-endedness for the sake of open-endedness. Now, while I completely agree that we need proper definitions of complexity and diversity in this kind of work, I completely disagree with his conclusion that we should not engage in, and there's no value in, the quest for open-endedness for the sake of open-endedness. And I hope to show you in the rest of this talk why I think that. So, in my paper in the Artificial Life Journal, I presented a high-level conceptual framework to help orient the discussion and implementation of open-endedness in evolutionary systems. There were 3 main components to this framework. One was an attempt to properly describe what open-endedness is in terms of innovations, and I made this distinction between exploratory, expansive, and transformational novelties. The second component was a formalism of the basic properties, basic processes of evolution in terms of the generation of the phenotype, the evaluation of the phenotype, and the reproduction with mutation of the phenotype. And the third component was the distinction between intrinsic and extrinsic implementations of these processes. So these types of novelties, the first component, you can loosely think of them as the extent to which novelties are of the more of the same variety versus more fundamental and unexpected innovations. So if you look at the picture on the left there, the top case, exploratory innovations, is basically just a continuing search of a given phenotype space. Whereas the other 2 types of novelty, expansive and transformational, involved the discovery of door-opening states that in some way open up new possibilities for phenotypes which weren't there before. The second component of my framework was this formalism of the basic evolutionary processes. Now, there's nothing particularly new here, but I was just wanting, in the way I express these processes, I was wanting to emphasize the interrelationships and the parameters that can affect these processes. So, for example, with generation, a phenotype is produced by a mapping function from the genotype, which depends upon L, which is the laws of physics of the environment, and has parameters including the genome, G, the abiotic context, Ca, and also the biotic context, Cb. And similarly for evaluation and reproduction with mutation. The way I've expressed these things indicate all of the influences that might affect, or at least the most important influences that might affect these processes. In order to get continued search of a landscape rather than just optimization of a static landscape, you need to shake up the adaptive landscape of the system. And in my journal paper, I looked at the ways in which the organisms within the system could do that by themselves, basically by modifying one of these 3 evolutionary processes, either the function itself or the parameters that affect that function. So I came up with this mapping of all the possible ways in which a phenotype could do this, and showed how those related to various topics in the theoretical biology literature. Now, interestingly, it turned out that all of the mechanisms on that diagram give rise to exploratory open-endedness only. That is to say, they describe how an evolutionary system might continually search a given phenotype space. But the more interesting cases of expansive and transformational open-endedness require other considerations. Now, those considerations include: where does this extra space of possibilities come from? And how can the evolutionary system access the new states via intrinsic mechanisms? So in the paper, I gave some answers to those questions involving concepts such as domains, exaptations, trans-domain bridges, non-additive compositional systems, and a more sophisticated treatment of the concepts of behavior and semantics. But having set out all of that, I came to the conclusion in my journal paper that open-ended evolution fundamentally comprises just two essential processes. One is the ongoing exploration of a phenotype space, and the other is the discovery of door-opening states in that space that open up expanded phenotype spaces. So that's a framework I set out in my journal paper. Now let's have a quick look at Hintze's model. So he described a very simple world, it was a discrete 2D world in which agents started off in the center of that area and followed a trajectory defined by their genome. The genome was just a sequence of symbols right, left and forward. And fitness of an agent was determined inversely proportionally to how many other agents had travelled across the same locations. Now, having run this model many times, Hintze observed that the complexity of the agents' genomes, as measured by the zlib compression size, increased exponentially. He also found that the diversity, at least as measured between runs using randomly chosen agents, also increased exponentially. So he concluded that his model fulfilled all of the hypothesized requirements for open-ended evolution suggested in several previous publications. And instead of calling open-endedness a solved problem, we need to focus our attention on the definitions that allow this simple model to be sufficient. And so the question now becomes, how can we define complexity and diversity in such a manner that one could have rejected this model with ease as a candidate for open-ended evolution? Well, in response, I'd say I'm not sure that of his claim that his model fulfills the hypothesized requirements. I think he's misunderstood some of those requirements, but in any case, that's not really the main focus of this current paper. I do agree that it would be beneficial to focus our attention on the definitions that allow this simple model to be sufficient. But I don't agree that the question now becomes how we define complexity and diversity. At least that's by no means the only question. It is an important question, but there are also questions of the mechanisms for ongoing exploration and also the mechanisms for discovering door-opening states in his model. So, does it have mechanisms for ongoing evolution? Well, yes, it does. And if you consider all the routes that I mapped out in my earlier diagram, it just has one. That is, a phenotype can affect the fitness of another phenotype because the fitness function is defined in terms of how many other agents have crossed the same locations in the environment. So there's this degree of biotic context in the evaluation function. And so the extent to which Hintze's model does show open-endedness and ongoing search comes about through this one process out of the many others that could have existed. There are things that can't happen. There's no possibility for the genotype to phenotype map to evolve, or for the reproduction and mutation operations to evolve. But nevertheless, there is this one simple way to allow ongoing exploration. Now, how about mechanisms for discovering door opening states to expanded phenotype states? Well, basically, there aren't any in Hintze's model. The semantics of action are encoded directly into the genes, left, right, and forward. The action of the genes is strictly additive. If you take two sections of a gene and put them together, they have the same effect as those two sections alone. And there's not really any interesting dynamics in the world. There's no laws of physics allowing the possibility of action beyond what is directly encoded in the genome. Now, there's a lot more that could be said about this, but for the purposes of this talk, I just want to make the point that open-ended evolution is not just about complexity and diversity. It's about the ongoing exploration of a phenotype space and the discovery of door-opening states that open up expanded phenotype spaces. There are many intellect topics that must be assembled to understand how to design and build open-ended evolutionary systems. And it's only by studying open-endedness for the sake of open-endedness that we might hope to make progress in this area. And with that, I will conclude. Thank you very much. And just a final word to say, please check out my new book. Thank you.